Hello, I am Abby Francisco, and this is my presentation on ATP pathways. So we'll start with ATP production from glucose, and we'll begin with one molecule of glucose right here. It will go through glycolysis, and the products of glycolysis are 2 net ADP and 2 NADHs. Now that one molecule of glucose will be split into 2 pyruvate. Remember that, that's 2 pyruvate. And so let's just take one pyruvate and when oxygen is present, it will go through pyruvate oxidation, where NADH is produced from NAD plus, and you have acetyl coenzyme A as a product. Now, acetyl coenzyme A then combines with oxaloacetic acid or oxaloacetate to form a citric acid. Now, this part right here is actually very important, and towards the end of this presentation, we're going to circle back to it. But for now, they combine to form citric acid and then continue on to the Krebs cycle. In the Krebs cycle, 3 NADHs from NAD pluses are produced, 1 FADH2 and 1 GTP. Now, the NADHs and the FADH2 will continue on to the electron transport chain, where they will be oxidized and produce ATP. Now, ATP production from fat. So we'll start with one fatty acid, in this case palmitic acid. And in order for it to be activated, 2 ATP needs to be released in order to create acyl coenzyme A. So again, 2 ATP released to form acyl coenzyme A, and we'll kind of circle back to that when we go over ATP yields. Now, once that fatty acid, palmitic acid, gets converted, it goes through this cycle called beta oxidation. Now, the first stage of beta oxidation is dehydrogenation, and the product of that is FADH2 from FAD and produces transenyl coenzyme A. Now, the second stage is hydration, where a hydration molecule is actually added, and hydroxyl acyl coenzyme A is produced. The third stage of beta oxidation is dehydrogenation again. Now, in this stage of dehydrogenation, NADH is produced from NAD plus, and ketoacyl coenzyme A is produced, and then it splits into myristoyl coenzyme A and acetyl coenzyme A. Now, beta oxidation goes through about 7 cycles. So it takes a little bit longer to produce ATP than glucose. At the end of the 7th cycle of beta oxidation, you have 8 acetyl coenzyme A. Take one from here, and after the 7th cycle here, you have 8, and it will bind to oxaloacetic acid, if you remember previously from ATP production from glucose, and then from there continue on to the citric acid cycle or the Krebs cycle, like what we discussed earlier. Additionally, we have 7 NADHs produced here and 7 FADH2s produced, which both of which will go on to the electron transport chain to be oxidized and produce ATP, just like ATP production from glucose. Now, so like I said, we're going to go over ATP yield from both glucose and fat. So from glucose, you have our 2 ATP from glycolysis and our 10 NADHs, 2 FADH2s, and 2 GTP. So if that sounds like a lot and more than what we had discussed in the first slide, remember that that one molecule of glucose got produced 2 pyruvate. So we discussed 1 pyruvate, and now we're adding the second pyruvate, and this is our total yield. Now over down here is our ATP key, where we have how much ATP is produced from what product. Now, if you add all of these numbers up, you end up with a total of 32 ATP from glucose. Now, from fat, the previous slide, we have our 8 acetyl coenzyme A's, our 7 NADHs, our 7 FADH2s, and if you remember in the initial part before beta oxidation, we did require 2 ATPs released in order to activate that fatty palmitic acid. So we're going to take out 2 ATP. So now we have, again, our key here. how much ATP is produced from each product, you multiply it by 877 and add it all up, we have a total of 106 ATP produced from fat. Now we can see that there is a significant difference between the ATP yield from fat versus from glucose, which we'll go over what that means later. Interaction across exercise intensity and duration. So there are differences between using glucose and versus fat as a fuel source. We'll discuss what glucose is beneficial for and what kind of exercises fat are using fat as a fuel source is beneficial for. So with glucose, this is where you're going to want to use short maximal effort exercise lasting no longer than 90 seconds. So that's that quick, immediate, powerful training sessions. Glucose can be used with or without oxygen. So aerobically with oxygen or anaerobically without oxygen. When glucose is used with oxygen, it supplies fuel for long duration, so think marathons. When it's used without oxygen, lactic acid is a byproduct, and glucose is able to be used anaerobically without oxygen because of glycolysis. So when oxygen is present, when oxygen is not present, we will use glycolysis, and when it is present, we will use the Krebs cycle or the citric acid cycle. Now with fat, it is the main fuel source for aerobic exercise. It does take longer than glucose to produce ATP. If you remember, we went through 7 cycles of beta oxidation. Fat also becomes the primary fuel source when intense long duration exercise depletes glucose and muscle glycogen. So when all of the blood glucose is used up, then we will start using our fat stores. So, for our long distance marathons, fat is a good fuel source. So because fat takes longer to produce, it is typically better for long duration exercise. So now, as in all things, we do have our limitations. So ATP production limitations from glucose. We have ATP and NADH as some limiting factors because when there is too much of either ATP or NADH, it acts as an enzyme inhibitor and it slows down the rate of ATP production. Additionally, glycolysis is limited by enzymes as well as oxygen. So if there is too much oxygen present, it actually inhibits glycolysis, and when glycolysis is inhibited, so is ATP production, because if you remember, after glycolysis, we have two net ATP produced as well as 2 NADHs. Now with fat, is the main limiting factor for ATP production from fat is actually carbohydrates. So it is dependent on carbohydrate breakdown. Now this right here is a little bit cyclical, so stick with me. Pyruvate levels are a big kind of factor here because when they're low, there are decreased levels of oxaloacetate and malate or oxaloacetic acid. And this is actually needed for the Krebs cycle. So that takes us to oxaloacetate. So if you remember in this slide, when I mentioned that this is actually important and we'll circle back to it, this is what we're talking about now. So here we're at oxaloacetate or oxaloacetic acid, where it binds to acetyl coenzyme A. So oxaloacetate is needed in order to bind with acetyl coenzyme A, and then proceed to the Krebs cycle, or the citric acid cycle. If it's not available, then acetyl coenzyme A has nothing to bind to, and therefore the Krebs cycle won't happen. Now, if we look back here at our total ATP yield, acetyl coenzyme A actually bears a lot of weight in ATP production. So pyruvate levels and the whole carbohydrate breakdown and low acetate is a huge limiting factor for ATP production from fat. So what does all this mean? How can we apply it to the real world? Why does it matter? So macronutrient choice of fuel source is really dependent on what you're doing, what the activity performed is, and the intensity level of that activity. So if we take into consideration glucose and fats, one might think, well, fat produces the most ATP. Why would I not always use that? Again, we have to consider the type of exercise, our fitness goals, and body composition as well. But to kind of tie it up in a nice bow, long duration activities, ATP from fat is more beneficial and powerful. That short duration, immediate energy activities that we need, ATP from glucose is typically more beneficial. But again, I'm going to emphasize that it is important to take into consideration the type of exercise, fitness goals, and body composition. For example, if you are working towards an aesthetic competition, you're not going to want to use a lot of ATP from fat if your goal is to reduce body fat percentage. Conversely, if you are looking to, get a power exercise in tire flips and plyometric things, then you're probably looking at ATP from glucose. And that is the end of my presentation. Thank you.